Hello everyone. Now in this lecture we will discuss the points of composition of functions. So in the previous lecture we have seen about the functions, means what is the definition of the function and its different types, like what is the one-to-one function, what is the onto function, and what is the one-to-one onto or one-to-one correspondence function. And also we have seen in the previous lecture that what are the inverse functions. So in this lecture we will see the remaining part of the inverse functions and what are the composition of functions. So in the previous lecture we have seen what is the inverse functions. So now in this lecture we will see some different examples of that function. So what is the question here? So let a is equal to 1, 2, 3, 4 and b is equal to small a, b, c, d. So there is a function is given from a to b. And what is that function? The pairs are 1a, 2a, 3d, 4c. So question is that find the inverse function. So to find the inverse function, so we will get a1, that is reverse a1, a2, d3 and c4. So here check, in this function inverse function the domain is a, the domain will be a, d and c. Okay, and what is the range or what is the codomain? The codomain is 1, 2, 3 and 4. So this is not function. Why? Because the condition is not satisfied or it is not the definition of the function. To make a function we have to make a unique element of the domain to pair with the codomain. So here the repetition of the domain is here a and a. So this is not the definition of the function. That's why we can say that this is not a function. Let's say another example. F is given, that is function is given 1a, 2c, 3b, 4d, and we have to find out the inverse of that function. So what is the inverse? a1, c2, b3 and d4. So we can say that all the conditions are satisfied. That's why it is a function, and which is a inverse function from b to a. Next, in the earlier lecture we have seen how we can find out the inverse of that function. Now suppose the equation is given and the question is given that find out that inverse of that equation, then how we can find that inverse of a function? So there are some steps are given to find out the inverse of a function. The first step is that replace the function f of x by y in the equation which describes the function. Second, swap the variables x and y, that is replace x by y and y by x or vice versa. The third step is solve for y, and the last and the fourth step is replace y by f inverse of x. Next, let's see some examples to find out the inverse of a function. So the question is given, find the inverse of the function f of x is equal to x plus 1 divided by x. So the question is given to find out the inverse of a function. So follow the 4 steps which are given. What is the first step? The first step is replace the function f of x by y. So step first, replace this f of x by y here. Okay, x plus 1 divided by x. So what is the next step? The next step is swap the variables x and y, that is replace x by y and vice versa. So the second step will be our y is replaced by x and x is replaced by y here. Then next, what is the third step? Third step is solve for y. Now solve this question and find out the y. So xy cross multiplication xy is equal to y plus 1. So after taking the y here, xy minus y is equal to 1, and take common of this. So y is equal to, x will be there and minus 1 is here, is equal to 1. So after solving this, we get the y is equal to 1 divided by x minus y. So what is the last step? The last step is that replace y by f inverse of x. Now here, replace this y by f inverse of x is equal to 1 divided by x minus 1. So here, after following the 4 steps, we got the answer f inverse of this x is equal to 1 divided by x minus 1. Now let's take another example. Find the inverse of the function. The function is given f of x is equal to cube root of x minus 2. So follow all the steps. What is the step first? Step first is replace f of x by y. Okay. So here replace f of x by y, we get y is equal to cube root of x minus 2. Now follow the second step. What is the second step? Second step is replace y by x and x by y. So here after replacing y by x, x is equal to replace x by y. So here y is y minus 2, cube root of y minus 2. So what is the next step or third step? Third step is solve for y. So after solving this, we get x cube is equal to y minus 2 is equal to x cube plus 2 is equal to y. And after solving this, we get y is equal to x cube plus 2. And the last step is what? Replace y by f inverse of x. So after solving this, we get the answer of this function. What is the inverse of that function? X cube plus 2. This is the inverse of this function, cube root of x minus 2. Okay. Now take the next point, composition of the functions. A composite function is formed by the composition of one function to another. That's why it is called as a composition of the function or composite function. So composite function is what? We get the composite function by composition of one function to another. So it refers to the combining of the functions in a manner where the output from one function becomes the input for the next function. Okay, this is the combining of the functions, means output from one function, it will become the input for the next function. So let f is equal to a to b and g is equal to b to c. So these are the two functions are given. F is equal to a to b and g is equal to b to c. So these are composed by first applying f to an argument a belongs to a and then applying g to the result. So a function h can be defined from a to c such that for every a in a is equal to h of a is equal to g f of a. So here the two functions are given f and g. F is from a to b and g is from b to c. So the composite function is h. So the function h is called the composition of the functions, or it is also called as a relative products of the functions. Okay, the composition function is also called as a relative product of the function. Okay. Next, the composition of a function f and g, it is denoted by g small circle f, that is g composition f. So see here carefully, this is the statement, the composition of a function f and g is denoted by g of f, means but denotation is G first and after that F is there. But how we can read this? The read how we can read this statement or read this symbol? The composition of a function f and g, that is g small circle f, but it is the composition of the function f and g, not g and f. So mathematically we can write this way. So it is one kind of the definition of the composition of the function. So if f is a function from a to b and g is a function from b to c, there are the two functions, then h is the composition of the two functions is equal to g of f, that is composition of the function f and g is equal to a and c, such that is a small a belongs to a set a and c belongs to c, and for small b some b, that is the existential quantifier, that is few b or some b belongs to b and b is equal to f of a and c is equal to g of b. So more precisely, G composition F is called the left composition of G with F. Next, here it is assumed that the range of F is a subset of domain dg of G, which is B. That is, a range of F, it is the subset of domain of G. Okay, if this is not done, then G of F is empty. Okay, so if we don't want that G of F is empty, then the condition is that range of F is the subset of domain of G. So any function G for which G of F or G composition F can be computed is said to be left composable with the function F. And in such case we can say that G composition F of A is equal to G of F of A, where A is in the domain of G composition F. So graphically, how we can represent the composition of the two functions? So see here, the composition of the two functions f and g. So here there is first function is there f, which is from a to b. There is another function that is g, which is from b to c here. So in this function f, the domain is a and range is b. In the function g, the domain is b and range is c. So in this set A, the elements are, or domain set is a1, a2, a3 and a4. In the function f, the range of f is b, which is b1, b2, b3, b4 and b5. Similarly, in the function g, the domain of g is b, which is the set b1, b2, b3, b4 and b5, and range of g is c, which are the elements or which are the set c1, c2, c3. So this a1 pair with b2, after that pair with the c2. So we get composition of the two functions, that is a to c. We get a1 to c2 here. So here a1 to c2. Next, this a2 pair with the first composite with the b1, then b1 to c1. So we get a2 to c1 here, a2 to c1. Similarly, a3 is a function from a3 to b3, after that b3 to c3. So we can say that composition of from a to c is a3 to c3. Similarly, for a4, a4 is function from if f is a function from a4 to b5 and g is a function from b5 to C2. So composition of the function A to C will be A4 to C2. Okay, so this is the representation of the two functions f and g graphically or diagrammatically. So here a to this is the function f is from a to b, g is the function from b to c, and this is the composition of the function resultant function, that is composition of f, f and g, that is a to c. Next, so here we can say that the condition is that the range of f, which is b, and domain of g, which is b, must be common. Then and then only we can make the composition of A to C. So keep this in mind or concentrate on this thing, that the range and domain of these two functions must be common. Then and then only we can get the composite function. Next, let's see one theorem. The composition of the function is associative. So how we can prove that the function composition of the function is associative? So for this proof, we consider the three functions are here. F is from A to B, G is from B to C, and H is from C to D. Then H of H composition, G composition F, and H composition G and composition F are the functions from A to D. Now it is to be proved that H composition of G composition F is equal to H composition G composition F. So to prove that we have to first assume that B is equal to F of A. So what is this B? B belongs to capital B, that is B is the element, B is equal to F of A. Similarly, C is equal to G of B and D is equal to the H of C. Means F is a function from A to B, G is the function from B to C, and H is the function from C to D. So we have to assume that first. Then after assuming we have already we have A, B belongs to F, means small a is the element of capital A, this A set A. Then small b is the element of capital B. Similarly, this small b is the element of this B. Small c is the element of this capital C. So it is similarly this BC belongs to G, CD belongs to H, and A to C. Okay, directly from A to C belongs to composition function G and F, or F and G. Similarly, we can say that BD belongs to composition of the function G and H. So by making the same argument, we can write like AD belongs to H composition G composition F. Similarly, it can be shown that AD belongs to H composition G composition F. So this fact being true for any A and corresponding D. So we have H composition G composition F is equal to the H composition G composition F. Thus, the composition of the function is associative. Okay, so this is one of the theorem in the composition of the function, which is composition of the function is associative. So this theorem, the composition of the function is associative, we can represent it in the diagrammatically. How we can represent this theorem diagrammatically? So here, see here, so capital A to B there is one function f. From B to C there is a function g, and from C to D there is one function that is h. So here after taking this function, the compositive function, how we can represent it. So here from B to C, G, and C to D, H. So the compositional function from B to D is equal to H composition G. That is composition of the function G and H. Similarly, see here from A to B there is a function F, and from G to C there is a function, B to C there is a function G. So the composition of the function from A to C will be G composition F. That is composition of the function F and G. So there is a composition of the two functions. Composition of the two functions are there. Similarly, from A to D, there is a composition of the three functions. So how we can represent it? From A to B, B to C, C to D. So there will be A to D, the function will be this F, and this H composition G will be H composition G composition F. Similarly, see here this curved line here. So composition of the three functions are here. A to B F, B to C G, and C to D H. So how we can represent the composition of the function directly A to D? So we can represent it like this way: H composition of G composition F. Okay, so this is diagrammatically a representation of the associative theorem. Next, so now let's see some examples how we can find out the composition of the function. Okay, so what is the question? In the question, A is given, that is set A is given 1, 2, 3, and B is equal to R, S, and C is equal to M, N. So function is also given f1 be a function from A to B, which is given by f1 is equal to 1r, 2r, 3s, and f2 be a function B to C, which is given by f2 is equal to rn, sa. So what is the question? The question is that compute f2 composition f1. That is, we have to compute, or we have to find out the composition of the function of f1 and f2. Okay, see here carefully composition of the function of f1 and f2, but how we can write it? F2 composition f1, but how we can read it? F1 composition, so it is composition of the function f1 and f2. So to find out the composition of this function, we have to consider first f1. Now after that we have to consider the f2. So see here the function f1. So in the earlier PPT, I have said that the composition of the function is nothing but the relative product. Okay, so this term is very useful here, because to find out the composition of the function, we have to make the relative production here, or relative products are here. So f1, the first pair is 1r. So see here the domain in this f1, in the first pair, domain is 1 and range is r. So take the f2, take the first pair rn of the f2. So see here the range of f2 is, domain of f2 is r and range of f2 is n. So here, so 1r and rn. So condition are satisfied, means range of f1, that is r, and domain of f2, that is r, are same or common. Then by deleting that common, we can take the 1 and n as our result, which is domain of f1 and range of f2. So we can get this first pair of our composition function. Similarly, 1r pair with the Sn, but here, so there are no elements are common here. That's why there are no pairing are here, or no composition here. Then take the second pair 2r. So pair with the first pair of the f2, that is rn. So here domain of f1 is 2 and range is r. Here domain of F2 is R and range is N. So after pairing we get the result 2N here. Similarly 3S and Rn. No pairing are no common elements are here. 3S and Sn. So common elements are yes. So we get the pair 3N. So resultant output is here 1N, 2N and 3N. So let's take another example for your better understanding. So question is A is equal to 1, 2, 3 and F1, F2, F3 and F4 functions are given from A to A. What are these functions? F1 is equal to, these are F2, F2 is F3 and F4. So these are functions are given and we have to find out that F1 composition F2, F2 composition F1, F1 composition F3 composition F2, then F4 composition F2, F2 composition F4 and F4 composition F4 and F1 composition F4. So how we can find out that F1 composition, for to calculate the F1 composition F2 we have to consider first F2 not F1. Similarly in the F2 composition F1 we have to consider first F1 not F2. So here in this question also in this question itself I have given the solution here. Why? But because in the next PPT I can't explain it better. So here in the question itself I have given the solution here. So see here F1 composition F2. How we can calculate this? Take the first F2. So F2 composition F2. So take the first pair 1 2 and pair relative product with the F1. So conditions are not satisfied. Take the first pair of F2 and second pair of F2. So here condition is satisfied because domain of F2 range of F2 is 2 and domain of F1 is 2. That's why 2 2 common and we get the element that is pair 1 3. Similarly 1 2 pair with the 3 1. So there are the no element are common range and domain. So take the next pair of F2 that is 2 1. Pair with the F1 that is 1 2. So here the one range of F2 and domain of F1 that is 2 is common. So we get 2 2 here. Similarly 2 1 pair with the 2 3. So we can't make the pair 2 1 and 3 1. So it is also not done. Then after that take the third pair 3 3 pair with the 1 2, not done. 3 3 2 3, not done. Then after that 3 3 and 3 1. So range of F2 and domain of F1. So range of F2 is 3 and domain of F1 is 3 common. So we get the pair 3 1. Okay, similarly make the composition for F2 composition F4. For this time we have to take F1 first and after that F2. So F1 is 1 2 2 3 3 1. So take the first pair 1 2 and pair with the F2. The first pair of F2 is also 1 2. Take the domain of F1, range of F1 2 and domain of F1 that is 1. So there are no elements are common. Same. Then take the first pair and F1 and take the second pair of F2. So here domain of F1 and a range of F2 are common. So we get the element are 1 1. After deleting that common we get the resultant 1 1 pair. We get the first pair 1 1. Similarly 1 2 with the 3 3. So there are no elements are common. Now take the second pair of F1 2 3 with the first pair 1 3. So no elements are common. Then 2 3 pair with the 3 3 here. So range of F1 and domain of F3 are common. So we get the pair here 2 3. Similarly 3 1, 3 1 and 1 2. So here the range of f1 and domain of f2 are common, so we get the pair that is 3 2. So for pairing with the other, so it is not done. So our result is 1 1 2 3 and 3 2. Okay, so similarly you can do this for all the functions to find out the composition of the all type of the functions, that is f1 composition, f3 composition, f2. Okay. Okay, thank you.